everyone. It's great to see you all here today. My name is Andira Schroeder. I am the Global Marketing Manager for Link3D, and we're excited to be a part of this Women in 3D Printing event today and help bring the community together virtually. So I'll hand it over to you, Kristin.
Great. Welcome, everyone. We're really excited about the panel today. I'm Kristin Mulherin. I'm the president founder of AM Cubed, and I'm also on the board of directors for Women 3D Printing. Today, we're here to talk about 3D printing in aerospace. Recently, the 3D printing world has obviously been very heavily focused on healthcare for good reason. And commercial aviation has obviously been struggling as a result, but space exploration has actually been charging ahead quite strongly. With that said, just as a bit of background, according to 3DP BM's recent report, in 2020, the AM market across aerospace is estimated at nearly $3 billion. But over the next 10 years, they predict that it's going to reach over 17 billion. So there's obviously quite a lot of opportunity for those within this industry. And I think this panel today is going to be a really interesting insight into where things are going to be going. Before we get to the introductions, I want to do a big thank you to our sponsors, Link3D and AlphaStar. Andera from Link3D, thanks so much. Like without you guys, it would be really, really stressful and difficult. And AlphaStar as well as one of our new sponsors this time around. So during the networking session, if you didn't notice before, you can look again after. There are links to both these companies on the primary tables on the outside. So if you want to learn more about them, you can go ahead and click on those links. As Andora said, don't forget to submit your questions through the Q&A panel on the right. And you can upvote other people's questions that you'd like to see get answered. One thing is just try to keep your questions based on the topic around aerospace in general, 3D printing, obviously. And be sure to stick around after the panel for additional time for networking. I'll also be introducing the details for the next panel at that point as well. So now on to the panelists. I thought we'd start off with each of you introducing yourself and giving us maybe a recent success story within AM at your company. Anna, do you want to go ahead and start?
Yeah, thank you. Thank you for that, Kristin. Yeah, so Anna Tomzynska, I am the Boeing Additive Manufacturing Chief Engineer based in Southern California. I oversee the additive insertions across the entire company from Boeing Commercial Aircraft, Boeing Defense Systems, and Boeing Global Services. And so also leading initiatives to mature the technology with different respective areas within metal and polymer additive.
Recent interesting stories to share from what's going on?
And then, an example that I'll use is what Boeing had launched last fall was the first 3D printed RF antenna. So it's an antenna that commands the satellite in orbit for 15 years. It turns on all the power electronics, all the electric ion engines, and it has to have a reliability to function in orbit for 15 years. But then the neat thing is we're used to seeing 3D printed structures, right? So this would be one of our first electrically functioning 3D printed items that we've qualified and certified for space flight.
I think maybe hopefully we can get a little bit more into that kind of detail later. Deb, do you want to go ahead and do your introduction?
Yeah, sure. So my name is Deb Whitis. I've been at GE Aviation for over 25 years now, 26 years. And my current role is the Chief Consulting Engineer for materials across all of aviation, commercial, military, and marine and industrial components. And I also, before this, managed the materials organization at GE Additive, which was born in early 2017, which is a group within GE Aviation that's focused on manufacturing machines and materials and providing services for the additive community. And in terms of the new things going on at GE Aviation, so you've probably heard about the fuel nozzle, but actually that wasn't the first component that was FAA certified. So there was a T25 sensor that was originally certified back in 2015. And then our latest component is a what's called a PDOS, or power door, I got to make sure I get it right here, power door opening system is PDOS, bracket for the GEnx 2B that was just approved. And we've got about 20 more components that are about to be certified between our GE9X engine and our GE Catalyst engine that's coming out.
Great. Eliana, do you want to go ahead?
Yeah, thank you. I'm Eliana Fu. I'm Senior Engineer for Additive Technologies at Relativity Space. If you haven't heard of Relativity Space, we are a pretty new sort of tech startup based here in Los Angeles. We're actually moving from Inglewood, which is right now next to LAX, down to Long Beach. So we'll be near a whole bunch of other space companies near the Long Beach airport. Our mission is to fully 3D print and launch a rocket. And so lots of people in space exploration these days have 3D printed parts, but we're the only ones who say that we want to 3D print everything. So some major highlights for you. We recently announced, well, back in October, that we successfully completed Series C funding. So we're fully funded till first flight. New investors also include Tribe Bond Capital and the actor Jared Leto. We also announced a couple of weeks ago, which you might have seen in the news, satellite customer Iridium. And we also announced that we have right of entry from Vandenberg Air Force Base. So we actually can take off from the Cape and from Vandenberg. So those are some quick highlights for you. I can't really name specific parts because everything is being 3D printed. So it's everything.
Well, let's get started. As I said, if you want to ask any questions, go ahead and put them in the Q&A and we'll get to those in a minute. But I kind of wanted to start off with a little bit of a general question in terms of what are the specific challenges that you're looking to solve using additive manufacturing and 3D printing in aerospace?
Well, I can start. This is Deb again. Hello. I think one of the big challenges that the industry as a whole is working through is, at least within the aerospace industry, is working on the quality of the machines, the consistency of the machines today. So there is, the machine makers are all working through this, and I think it takes a very strong partnership between the OEMs, the original engine manufacturers or equipment manufacturers, and those companies to really get to understanding what are the various sources of variation on the different machines, and to truly understand that and either work to make modifications to reduce those sources of variation, or to design around them to make your designs able to deal with the sources of variation that are there. That's probably number one for me. I don't know. What do you think, Anna?
Do you think that it's more of a, just a real quick on that, do you think it's more of a technology in terms of machine technology issue, or is it, who bears the burden of that? Is it the machine builders? Is it the software that accompanies it? Is it the material providers? Who do you think bears the biggest responsibility to achieving that successfully?
I think that's the struggle, is it really is everyone that needs to work together sometimes to get to the root cause of the different sources. And so, whether it's issues related to the machines themselves, the raw material, pre or post processing associated with them, I think it really relies on good communication both ways around the all people that are in the manufacturing process.
Mm-hmm. I guess that's the biggest trouble, like you said, is just getting everyone to be able to work together.
Yeah, and to Deb's point, I wanted to note, the consistency, being able to replicate the process consistently across many machine platforms. And this goes with partnering with the machine OEMs to have the machines under configuration control. There's FAA guidance that's issued that we really have to understand our tolerance bands, right? So any slight variation in laser power, how does it affect your mechanical properties? How does it affect microstructure, your densification? of your metal alloys is really what we need to understand and work with our OEM machine suppliers to develop a consistent process.
Yep. One of the questions I had actually for later was, what was the biggest hurdle you see to productionizing AM within additive manufacturing? I'm guessing that is probably one of the biggest ones there.
Yeah, I think so. You know, the whole industry is kind of working on developing standards today. But in order to develop those standards, again, you have to understand what are the critical levers in the process to control. So I think that's what the teams are going through now to define those so that proper industry-wide standards can be defined and used to show compliance to FAA requirements.
Mm-hmm. So we addressed it from the material or the machine builders and materials perspective point of view. What specifically within additive are you trying to, or within aerospace, what issues do you feel like you can solve, you can improve upon by implementing 3D printing?
A lot of part consolidation. So really finding those applications that give you a lot of benefit designing for additive, such as a good example would be heat exchangers, which is common across many companies and industry, where you're taking traditional solutions that have been brazed, that are costly, and you can design components for additive using that technology, and really bringing in the capability of internal cooling channels and features that aren't prevalent with the conventional technologies.
So the brazing and the part consolidation, I feel like my understanding is that's based a lot on improving reliability, so you have less joints. Mm-hmm. And then obviously I think weight reduction is a big one that we all are aware of in aerospace.
Right, weight reduction.
Beyond those two,
yeah, cost savings.
Yeah, okay. I was wondering, what are the other ones?
So business case would be the first and foremost, I would say, because anytime you bring in technology, no matter how much NRE cost needs to be associated with developing, there has to be a benefit from either a cost or a schedule perspective, and that's why additive is an advantage, and you have to find the right application for additive. In some cases, you'll find when you swap out a traditional aerospace component that's just a machine part, you're really not seeing the savings transitioning into an additive solution, but really finding those complex parts that would lend themselves well to the technology.
I think that leads really well into the number one question we have right now from the audience is why, for Eliana, why 3D print an entire rocket? Are there benefits to 3D printing every part?
Yes. So that's the whole mission of our company, actually, is to 3D print the entire rocket. It would be the first one to successfully launch a fully 3D printed rocket. But I think the number one word, which is the unique selling point of AM, is lead time. So basically, if I was to place an order for titanium sheet today, I mean, the last time I inquired on titanium sheet from the mill, it was 56 weeks. And then I laughed because I was like, I've been away from titanium for so long that I actually forgot that this kind of thing is normal. And so as a small company, you're facing, competition from all the other big aerospace established companies. They're like, wow, I can't really compete with that. What am I going to do? And it doesn't matter if it's titanium or if it's aluminium that you have to then bump form and then weld or friction stir weld or whatever it is, or make an isogrid that you have to machine out pockets, and that all those things take time. All those operations take time. And satellite customers want to get to their orbit now, or whatever their schedule is. I need to have this communication satellite in place for this project by this date. And so what you're buying is lead time. You're buying access to space faster for your customer. So that's really what it is. It's if I place an order for sheet, I can wait 56 weeks. But if I go and make a sheet, no matter how dodgy it might be, I've made a sheet. And so I've taken that out of someone else's hands and put it in my own hands. So the philosophy that we have at Relativity is for things that are established AM techniques, let's say laser powder bed, lots of people know how to do laser powder bed. So we are focusing on the things that lots of people can't do, which is a wire arc additive. There are very few people who can, we can send that out house. So that's why we decided to concentrate a lot of our effort internally on Stargate. So whenever you see anything coming out of press releases or anything like that on the news on relativity, you'll only ever see Stargate coming out, because that's something that we can't let anyone else develop, because we're the only ones who can develop it. So again, it's taking that responsibility back into our own hands so that we control that lead time. And that's the beauty of AM. That's what it allows us to do.
Just real quick, for those of us who don't know what Stargate is, can you give us a bit more detail on that?
Oh, sorry. Stargate is our wire arc additive. Our founders were two people who were interns at Blue Origin. And then when they graduated, one got a job at SpaceX and one got a job at Blue Origin. And then they were full-time designing parts and getting parts manufactured. And then we text each other saying, oh, this is so frustrating. Why don't we just 3D print the whole rocket? So they quit their jobs, started their own company. And fair play to them, because I didn't have an idea to start my own company when I was 25. But yeah, so the company hasn't been around for a long time, but we're already at 165 employees, and we're well on our way to designing a rocket for first flight, all using the basis of additive manufacturing as our philosophy. So Stargate is named after a character from the game StarCraft. I'm not a gamer, so I'm not really familiar with it. It's not Stargate the movie. Which is a portal to other worlds. Mm-hmm. But Stargate in the game is a machine that builds other machines. So that's why it's named.
Oh, cool. Okay. That's good to know. Well, it looks like we've got another popular question here. As aerospace companies, do you have plans on how to approach part qualification for critical parts? For example, trial and error, simulation software, machine agnosticism, etc. Anyone have an answer to that one?
Yeah, I'll take that one. Obviously, you want to, for any part critical or fatigue critical component, right? You do all the due diligence with qualification and certification testing. So at Boeing, we do a lot of environmental testing, mechanical testing from static to vibration, and just thoroughly, evaluating the application, the component, making sure it'll meet the end criteria. So especially for the first implementation with it, because it is a new technology, we take a lot of effort in doing our due diligence and understanding the performance of that component up front.
I think that's probably one of the things that's unique to aerospace more than anything else. Well, maybe healthcare as well, I suppose, but is one of the advantages people talk about with AM is the quick product development cycle and the quick prototyping to get you straight into bridge production and then into actual production. But at the same time, you have a lot of these restrictions that hold you back in terms of your qualification processes are a lot longer. How do you balance those two things?
Well, it's really understanding and working with the OEMs to understand, there's going to be inherent defects in the process, and really understanding those, what are those defects, what type of defects, and what Deb mentioned is you either design for them or you mitigate them by modifying the process in some fashion, right? But you really want to have the high quality component. We have, detailed processes and flows for qualification of, any additive component that would go on a commercial aircraft.
I think that leads really nicely into actually one of the next questions is, what is the process for getting FAA approval for additive parts? Can you give us just a general idea of what that process looks like and time frame and primary steps?
Yeah, I think at a high level, right, an additive component is no different than any other component in terms of the kind of substantiation that is required by the FAA. So depending on the particular type of component, there may be different levels of substantiation. But, for any new material, which this is how, you're treating this, is a new material, it's not cast, it's not forged, it's additively manufactured. And so we would have, a standard technical readiness level and manufacturing readiness level associated with that. And through that robust process, we define, again, what are the sources of variation, and then put in place plans to control those, and then do extensive testing, mechanical testing, to understand what is that variation, so that you're providing the design community the appropriate level of understanding for that material. And then, continuing that through, not just making coupons, but making actual parts, and then going through some kind of engine test for those components as well. So it can be quite a number of years, quite a lot of money to do all of those activities. But as Anna and Eliana mentioned, there are significant benefits to using additive components. And I'll say, even in addition to speed to market and low weight, in many cases, there can be actually improved performance in the way that you can design a component that maybe has a more organic shape. Anna talked about heat exchangers and making, multiple parts into one part. There are some real performance benefits that you can get that way too. So again, there's a lot of cost and time that goes into certifying a component, but it's for good reason that it buys its way onto the engine in terms of the performance or weight benefit.
That makes me think of one of the things we didn't talk about earlier is one of the benefits is flow, controlling flow and improving flow, either fluid or gas or whatever. I think that there's a huge advantage of that with additive as well. Is that something you feel is one of the primary advantages?
Oh yeah, definitely. Definitely going, back to the heater exchangers example, you can have internal cooling channels or different features, unique features. With new software platforms that are available out there for topology optimization, but, not only for topology optimization, but build simulations as well to make sure you can actually build that optimized component, because in a lot of topology simulation tool suites, you'll find that you can have a really neat additive component, but when you try to print it, you're going to have failures because of support structures, right? So it's really tying those two things together.
I think that's a really important distinction. Yeah. Sorry, go on.
Yeah, there's been a lot of advances in some of the product definition tools, just because people are trying to translate, what's in their brain and the novel organic shapes that now they can make, to translating that from the design space into a machine that's going to print it. So there's a lot of translation activities that have been spawned and improved software.
How far along do you think we are on that? Because I think it's really interesting. That's something that I haven't heard people point out as much as, the big hot topic right now is generative design and topology optimization and all of this. But just because you can create this thing in the software, it doesn't mean you can print it. And that's something people just don't talk about really very much. And is that because we're not very far along with that simulation, or why do you think that's not talked about as much?
I suppose if you had a computer, a product definition person, they would highlight that. But I think it's, I think that at least within GE, I think it was something that the teams dealt with early on. I don't think there's an issue today as much with that, but it was certainly a challenge.
Through experience and hands-on learning, the process evolves, and as people master the design for additive, it just gets, simpler going forward. So
back on a more of a general topic, other than the things we've already talked about, what are the biggest issues that we're currently facing in additive, specifically to aerospace? I know earlier when we talked, being able to print very large parts is one. I think that we feel, what are some other ones? Or expand a bit more on that, maybe Eliana, I know you had an opinion on that.
Yeah, I was sort of thinking about this one overnight, and then, a couple of things that came to my mind is that we were talking today about we are still hiring during the time of COVID, and COVID's affected a lot of space and aerospace companies and people that we work with, suppliers and such. the economic downturn is really, really shocking to the supply chain. Like you're almost scared to pick up the phone and call somebody and like, are they still there? Every time I send an email, oh, am I going to get a reply? And that's pretty terrible. How do we keep up the fast pace of AM iteration and design and testing? Because we are testing our engines, we're testing processes, we're testing Stargate, we're building out our building in Long Beach, we're installing the robots. How do we keep that pace up when we have to do sort of like physical distancing? We have to get people on site with negative COVID tests and all that kind of thing. So how do we keep hiring people when we can't physically interview them, or they're across the country and they're a good candidate? So all of those things actually affect our rate of building, believe it or not.
Any other issues you guys are aware of currently right now in additive and aerospace that we haven't touched on?
Well, I was going to touch on the fact that there's, people talk about there's only a few materials, or the material suite is limited for aerospace. I think there has been a lot of work on the standard materials that we use, but it is a small number compared to all of the different materials that we use. So as we get more experience with additional materials, it opens up more opportunities for expanding additive use to other components. What I will say is that I think there are a lot of opportunities to find new ways to reduce the cost and the time to bring additive materials suites to be able to be used. And I think there's, again, with collaboration between OEMs and universities and machine makers and component makers, that we will work on this. As I mentioned, it does take a lot of time and dollars to do all of this testing that's required for substantiation with the FAA. I think if there were opportunities to make that easier or less costly or faster, that would be a real benefit to expanding.
Yeah, and I would mention, leveraging industry and consortiums like NIAR and CAMP in generating allowables, right? That would be standard across industry for all, aerospace companies to utilize, rather than having each company come forward with trying to create their own set of design allowables, right, for the additive technologies, because that would truly help scale additive across the board.
You touched on just a minute ago, the materials, and I think we all, when we talk about aerospace, we think about metals. I think that's what we're generally talking about. We're talking about powder bed fusion. We're talking about DED in the larger formats. What about polymers and ceramics? So I think especially ceramics. How are you guys utilizing polymer and/or ceramic 3D printing within your companies? And which are you using it for flight hardware? Where are you using these other materials?
So Boeing has actually flown over 70,000 3D printed parts, and I would say 90% of those are polymer additive components on our various platforms. I would say, the metal additive, it has more of a challenge, understanding the process, its reliability. So that's been, one of the challenges, but we have a long history in flying polymer materials for about 2 decades now. So it's kind of a standard process for us.
What kind of parts are you flying made out of polymer 3D printed parts?
Yeah, they would be mainly non-structural loaded components.
How about ceramics? Have you implemented ceramics much yet, or is that still too new a technology? I feel like, Eliana, if we're going to print a whole rocket, some of it's got to be ceramic. No?
Yeah, right now we're just concentrating on metallics. We're fully aware that there are other materials like polymers, ceramics, glasses, and other things like that, but we're not really focused on them because our first mission is to get to a first flight. So we're not even aiming for a reusable rocket right now. We just got to get up. We'll worry about getting back down some other time. So, but we are fully aware that people are very interested in printing things with ceramics and polymers. They printed on ISS because they have a made in space printer there. So they've made widgets and tools and spare parts and things. And we also have like a little tiny mark forged at Relativity. And we do the same. We print like little widgets or blocks and things like that that help us with maybe fixturing or things that never leave the ground. So those things are really helpful, actually. You know, you want something quick and easy. And being a startup, we're pretty scrappy, so we turn things around pretty quickly. And we're like, oh, if that didn't work, okay, we'll just print another one. So no worries. So that's the kind of thing that's very cool. And then the thing that some people are even forward-looking is printing habitats off-world. Mm-hmm. So whether they're on the moon or on Mars, there's artist impressions, and there's people putting forward the idea to certainly be printing in different materials other than metallics. The question is, what do the feedstock look like, and is it inherently dangerous to bring it up there, or can you locate it when you get to the other off-planet, wherever it is, an asteroid or whatever? Can you use, you know, what's in the asteroid belt on Ceres, for example? So those are very, very cool questions.
Deb, how about GE Aviation?
So certainly there's a lot of polymer printing that's done for prototyping and also for tooling or masking. So not so much in production components as Anna talked about it at Boeing, but certainly there's a number of polymer printers at the Additive Technology Center in Cincinnati that are always humming. I think on the ceramic side, there are many industries that are currently making use of polymer printing, whether that's binder jet or DLP, and certainly something that GE is looking at for the right application within our business.
So just as a follow-up to that, one of the questions on the Q&A is what is the % breakdown of materials that your teams are exploring for AM between metals, ceramics, composites, and plastics? I think we know Boeing, you said, is 90% is plastics. What the rest of you guys, and it sounds like Eliana, you're pretty much 100% metals. How are you, Deb?
Yeah. And we're, you know, today I would say
okay.
99%.
That's really interesting that it's so different between Boeing and GE Aviation. I'm guessing obviously it's based on the ultimate end applications. Why would you say it's different between the two?
It gets pretty hot in the aircraft engine.
Yeah.
Interesting. Is it because, Anna, is it because most of yours is being used more in commercial versus? Yeah.
Right, like interiors or, you know, those types of
Okay, yeah, that's interesting. I wouldn't have expected to be so divergent between the two companies. So one question, I think you mentioned, Deb, earlier about the fuel jet nozzle. But one question here that's a lot of people that voted is, how has 3D printing changed the engine manufacturing for GE?
So, you know, I think it did start with that LEAP fuel nozzle, but it quickly evolved into a kind of a new way of thinking about systems design. So, you know, you can look at an individual component and say, hey, is this good for 3D printing? Look at the loads on it, see if you can reduce weight. But I think when someone took a team and pulled them together and said, you know, how would you redesign this whole system with the benefits of being able to additively print some of these components, that's where you really get into the ability to, as Anna said, combine different components into one. You know, I'm sure Eliana is learning about, you know, when you take a fresh sheet of paper and say, how do you design this system without the limitations, the shackles of conventional manufacturing, it really makes a lot of things possible that you never would have thought before. You know, being able to route air through components as opposed to having separate ducting. You know, a lot of opportunities come about through that. So I think we've made a lot of progress from, you know, the early days of just saying, hey, is this a feasible manufacturing method, to, you know, how do we actually change the design of our systems based on the capability to have this manufacturing method. I think it becomes so much more powerful when you're looking at you know, not just at a component level, but at a system.
I think one of the conversations I have more often than almost anything else is the fact that when it comes to additive manufacturing, we're not necessarily, like, the machine builders are not necessarily competing with each other. The material providers aren't necessarily competing with each other. The biggest obstacle we all have within this industry is educating the people to design for additive versus, you know, having traditionally designed for CNC or MIM or injection molding or whatever. Would you say that that's the case for you as well?
Yeah, in fact, there's a story that Josh Mook at GE Additive used to tell about a principal engineer. So he's a control title engineer, been with the company for many years, traditionally very good at designing a particular component. And he was kind of taken out of his regular team and dropped into this additive team to learn. And he said it took about 6 months for him to kind of unlearn all of the, again, the traditional manufacturing limitations that design engineers naturally put upon themselves to be able to, you know, design within a reasonable, feasible space. And he said, you know, when those limitations finally broke free from this guy, he was one of the most creative designers for, you know, novel things that you could do with the technology of the whole group. But it does take time. And I think education is a big part of this. You know, how do you take folks that have been designing the same type of component for many years to learn this? And in some cases, you have different teams that may not have as much experience in those components, and allow them the freedom to come up with some new designs. And then have those two teams come together, right, to make sure that it's still a feasible component. But yeah, it's a challenge across the different.
I like that you used the phrase "unlearn." That was something that came up on the last panel was on design and innovation, and one of the panelists, Katie Tucker, she talks a lot about that, and it's about before you can start to learn how to design for additive, you need to unlearn your old habits. Essentially, it's like it's just breaking old habits. And I think if you've been doing it for quite a while, it's quite difficult and sometimes a little bit scary. But once you can get through that, then you can the options are almost unlimited.
Yeah, we have teams of people with early career engineers that have come on board designing for additive, and they honestly don't know how to design now for the conventional method, right? Your drill depth, you know, the radii, right? And just those conventional methods are all gone for these new teams that are forming, which is great to see because that really opens that opportunity space and creativity.
I like what you said, Deb, as well about bringing the two different teams together, though. I think that's a really good way to come up with, you know, I mean, ultimately at the end of the day, we're all about, women in 3D printing is all about diversity, and the idea being that that's how you truly become innovative, is to have a really truly diverse team. So I think having those two teams that have very different backgrounds, I think that's where you're really going to drive some interesting things forward. One of the questions popular that I think is also really interesting, especially because I think you all three will have pretty clear answers, is what do you see as the ratio between doing things in-house, where it sounds like Relativity is mostly all in-house 3D printing, versus outsourcing to service bureaus and places like that? Or not? Apparently, Eliana, it's not.
Yeah. Well, it's really interesting. And there's also a question about using people like Geffatech. So I'll combine those two questions if I may.
Great.
So we're putting all our energy and focus on Stargate, the wire arc additive process, because there isn't anybody we can go to for a service bureau that can build a 25-foot long barrel section using wire arc, and that is a fact. So what we've discovered is by doing it ourselves, we've actually made tons of learnings And the learnings, obviously, then we're not going to share that with anybody because that's our IP, but it's also something that's going to help us iterate faster and get faster and faster and better. So all those things are really great. Where we choose to send things out, it's where it makes sense. So for example, we don't need to put a lot of time and effort reinventing things or processes for laser powder bed, because there's probably 10 people out there, in the US, that can probably do it better. And they have everything they have powder storage, handling, they have flow measurement, they have post-processing, machining, support removal, tumbling, heat treating. They can take care of the whole thing. So let them have it, let them do it, because they're already qualified for GE, Honeywell, Boeing, whoever it is. And then so we're good. We know you guys can do it, so we'll give you business. But then in that way, that's cool too, because everybody's getting better. So then the supplier also learns something new or sees a design that they've never seen before and go, oh, okay, now I can do this too. I can learn something different, or I can do this faster. And so the reason why we do a lot of stuff in-house is we're going at such a speed on some technologies that nobody can help us with, on other things where people can help us and we recognize they're the expert. You guys do it. And we're confident in that. And then that way there's a equal and balanced sort of spread amongst all those AM products. What you keep in-house is the stuff that's really hard to do, and that helps you get better. But the stuff that a lot of people know how to do and do well, and do, they received an award from GE or Boeing or whoever, top tier supplier. Okay, good, I have confidence. So that's okay too. So that's where the idea is. It's hard to put a percentage number on it because we move so fast, it could change overnight. So that's why I'm not going to put a number on it, but that's the rationale for that whole sort of process.
Deb or Anna, do you got something different to offer from your companies? I mean, you guys have come from such different size of companies. I'm wondering if it's different between you two, or I'm sure it's different between Relativity.
Yeah, so I think the general message is still the same. I mean, there's, as Eliana said, there's certainly difficult components that there may be some IP related to the manufacture of those that we would want to keep in-house. But for components where, again, the difference, I think, in at least in my case is, I talked a little bit about the specifications meeting FAA requirements. Those requirements many times have the manufacturing process and controls in place as part of that substantiation. So I think as an industry, as we gain more confidence with those machines and with what are the right requirements and standards around AM, I think you'll see more opportunities for things to be done outside the OEMs. There is a lot that is done, I think, internally today because we're still generating those standards and specifications that then we would use to work with the outside vendor. I don't know if it's different on your end.
No, it's
Anna.
pretty much, very similar, where the high IP is kept internally and then outsourced. But then also in commercial aviation, we don't want to be limited in our supply base. So we really want to scale and have many suppliers, so it's not single sole sourced. So working to get, scaling out.
How difficult, if you're a service bureau, how difficult is it to get your business, for lack of a better word? Is that process long, the certification process? Is it months, years?
It's demonstrating that a quality process, right? Very minimal defects, right? And being able to get qualified to our material and process specifications. Sometimes it could take a long time for a supplier to get qualified. And other times, depending on the supplier's experience, it could, be a matter of months.
Well, switching gears a little bit, I think is a great question. How do you prioritize what you want to attempt converting to AM next?
Yeah, so I can speak a little bit to that. I think there's, and Anna touched on this a little bit earlier, is, you have to have a very good criteria for how you're screening different components that may be good opportunities for additive. Because we just, we can't work on everything. So there has to be some rack and stack of the different opportunities that there are. And so, having a good cost model for what your company is developing, I think is key. And getting agreement on, what are the assumptions that go into that in terms of the different kinds of modalities, the speeds of the prints, the input costs of the material, et cetera, and then the benefits that those components bring is critical to being able to decide what to go forward with and what things to wait on. So, I know today we have, in addition to these additional 20 components that are going to be certified over the next year, there's over 80 components that are getting ready in development. And that's kind of a running list of components that then get racked and stacked to define, which ones are going to go into development next. So getting agreement on that cost model, I think, from all parts of the organization. So this isn't just engineering and all parts of the manufacturing and business side of your organization is really important to be able to help decide what is that next application going to be.
And they're usually the results in really complex components, not your angle bracket, right? It's all your system level components that really lend themselves to additive.
I think it goes back to always the same one.
Engine thrusters, right, for Eliana and those types of applications. So the one thing I would comment on, with certification, as Deb and I had, pointed out, we do have strict FAA guidance, but within Boeing also, we have the ability for within the space and launch division, with one-time use applications for additive, that's where you have, you don't have as perhaps, stringent criteria like Eliana if you have a one-time application, right? So you can test the component, vibratory test it, right, and then launch it, which enables early insertion.
Yeah, basically, if you're not worried about manned flight, or you're not flying for a NASA flight or the Air Force, and you're just doing commercial unmanned, then yeah, your window's a lot wider. But then again, you do want a successful launch, so you want to make sure you get to whatever orbit that you're trying to get to. So, at least has to survive a vibratory load on launching, and then even transportation or sitting on the pad for 14 days or whatever it is. So we do have to make sure that they're robust enough for that. But other than that, do we have to worry about, really, really high cycle fatigue or anything? Probably not. Maybe, in the short window of time, 14 seconds or less than that it takes to go supersonic. I don't really know. I can't remember all my GNC, but yeah, that's the kind of thing where we can take a little bit more risk, and because we're commercial, we don't have all those other restrictions. I'm sure that's going to change if we ever start taking NASA missions and things like that.
I think it's a great question, because I think actually, I know Deb and Eliana, your backgrounds are quite heavy on materials. Designing new materials seems to be a necessary task to address complex applications. What is your vision on designing new materials?
So that's one of the really fascinating parts about additive, is because it's a new manufacturing process, really different from forging or casting. It's kind of a micro casting machine, really. It gives you the opportunity to play with the chemistries of our standard materials to be able to influence the ability to print, and then ultimately the capability of that component. So there's a lot of opportunity there. I think the challenge within the industry is, as I said, before, scaling up and certifying that new material for an application is costly and takes time. So there has to be the appropriate level of benefit that new material provides in order to offset that cost. But I think there's a lot of, across the additive industry in general, and for aerospace specifically, where there are opportunities for new materials to, again, take advantage of the better printing capability and eventually better mechanical properties.
Are you doing this kind of work? Are you doing much of it in-house, or is it mostly you're relying on the material suppliers to do it?
For us, it's mainly internal today, but there certainly is across the industry folks that are working at the material suppliers as well.
I imagine, Eliana, that since you guys have essentially your own proprietary printing, Stargate, are you having to develop your own materials as well, or are you relying on off-the-shelf materials, so to speak?
Actually, we started with off-the-shelf materials because we wanted to prove that the technology was sound and weldable, for example. So we started with things like a 5000 series aluminium weld wire, which you can find from anyone. But as time goes on, you want more flight-like material, so you do want that to be a stronger material. And then you go out to the material producers, oh, we don't have that. And so, you kind of have to work together with R&D, but then they want to know what the business case is, and they want to know how many rockets you're going to be flying and what's your projected over 10 years. And you're like, well, I think it's like this. And then they do the calculations. They're like, that's crazy. That sounds ridiculous. And no, actually it will happen. And it won't just be us. There will be other small, tiny space rocket companies that want the same thing. And so if you can try and get the materials supplier to have that in mind, because don't forget that half of these or more of these people are the same people who make sheet, billet, bar, plate, and coil, and have been doing so for 100 years or whatever. And so they may have, certain amounts, dollar numbers of sales in additive manufacturing products, or products that go into AM, gas atomized powder or wire, whatever. Or maybe they're a wire producer that don't have a clue that it's going into additive manufacturing, and they just keep seeing these sales and they're like, oh, I wonder what that company is. We should investigate a little more. I think that a more joined up approach, not just between the end user and the metals manufacturer, but the person in between who's going to be using that input material, whether it be in-house or out-of-house at Service Bureau, or a machine manufacturer, let's say if it's laser powder bed, because not everything can be made by AM, right? So there are some materials that are so expensive in the current form that they are for AM, it doesn't make the ROI make sense. So if I want to build a second stage vacuum nozzle, I currently can't, because all the designs are in AM, are using a material which is 40 years old and only made by one person in the US or something like that. And so there are all these limitations and things like, oh yeah, the idea of using 3D printing is so amazing. And then you come to a complete roadblock because you can't even get the metal. You can't even get the material, the input stock. And then if you have the input stock, you don't have a method to adequately build it and then do the post-processing. So it just dies on the piece of paper. So that's the kind of thing that I've been chasing for 2 years. And I will keep doing it until somebody wants to take that challenge of, okay, so it's chicken and egg situation. And it's also the same for 718 or Type 64 or whatever. Those are 40 plus year old wrought product alloys. I remember when I was at SpaceX, we actually went to visit Stan Abkowitz, and it's like, wow, that's cool. He was like, I can't believe it. Materials on all these rocket ships going on. Yes, it's happening. But don't forget, that's an old material that's designed for something completely different. It just happens to be able to be melted and solidified in laser powder bed, so that's why it's used. But I'm sure there's something better, and that's what we want to get to, are the things that are better, right?
Yeah, that's great. Do you have anything to add, Anna?
Yeah, I was just going to mention, same with the Inconels, they've been around for, many decades. But yeah, working and partnering with the material suppliers to, always of interest is the higher strength, higher performance material systems, right? And so it's where is there an opportunity to partner and leverage the development efforts that are currently out there, right? And then what makes sense to develop internally, right? But definitely utilizing what's existing and already out there is the goal.
Well, we just have 5 minutes left. I think it'd be nice if we just took this last 5 minutes, if you could each just maybe give a little bit of insight in terms of what you hope to see happening in the next year or so within aerospace and additive, or something exciting that you think is going to be happening. Any last words?
Well, I'll start. I think that there's, again, on the theme of machines and stability, I think there's a lot of opportunities for, as software and the capability to do process monitoring becomes more embedded in the machines themselves. I think that's going to be a big help for the industry in general, in terms of the capability for repeatability and consistency of the product. So I'm really excited to see that come into the variety of machines that are out there. And yeah, just very excited to be seeing and be a part of the implementation of this technology into some real components, and to see what's possible for the next generation of aircraft engines that will start to really change their system level designs based on this new manufacturing process.
Mm-hmm. And really taking advantage of the art of the possible. Right now we are very limited into our build volume, 9 inches by 9 inches or 15 inches by 15 inches, right? And with Eliana's pointing out, the large format printing is really going to open a lot of opportunity space, but with that comes along, material consistency across the size of that component, and just really, opening up that opportunity space, because there's a lot of advantage that additive can bring in, whether it's optimizing our current platforms or designing new platforms, which would capture a new market space.
Yeah, and for me, I think you're going to see additive manufacturing or 3D printing become more and more common parlance. You're going to see people in the street will be talking about things that are 3D printed. I mean, we've already seen what 3D printing is doing to fight against COVID, printing things like face shields and visors and things like that, or ventilator systems. And even aerospace companies, I'm going to say like Virgin Orbit, try to help in fight against COVID by turning over part of their organization to actually printing ventilator parts. So actually, I think this is a great technology that reaches across not just space exploration or air travel, but also all these other sectors that we haven't even talked about. I mean, I know the topic of conversation today is aerospace focus, but aerospace is driving all these other sectors, because we're like the ones who will stick our neck out and say, this is a technology we believe in. So, I mean, from Relativity's point of view, that's like our whole mission. So you're going to see more and more, and also at the home market, people buying 3D printers for the kids so that they can play with, learn how to do design, learn to make toys, widgets, crafts, games, all kinds of things. And that helps with the learning, so that when they're ready to go into college and enter the workforce, they're used to it. It's completely normal to them. And also, it lets people become business owners and entrepreneurs, which they could never have done before. If I wanted to make my own forging company, it'd be really hard for me to go out and get a 500-ton forging press, but it might not be so difficult for me to go and get a 3D printer off of Amazon or Matter Hackers or somebody, right? So yeah, that's how I see it.
That's great. And I think it's a perfect way to end it as well. I think, and if any of you entrepreneurs out there, reach out to me after the fact, because I'd love to have, I was speaking to someone before this in the networking session, and I think there's a lot of really interesting entrepreneurial opportunities out there with utilizing additive manufacturing and 3D printing. And I think I'd like to highlight that on this panel as well at some point. So thanks, guys. I think this was awesome. Well, thank you so much for taking the time to do this today.